More of the Class A BJT amplifier. So we left off with cutoff and saturation. As previously mentioned, when the base current is equal to zero, the transistor is in cutoff. Under this condition, there is a small amount of collector leakage current, ICE0 or CEO, due mainly to thermally produced carriers. In cutoff, both the base emitter and the base collector junctions are reverse biased. So they talk about these thermal states. Typically, when you power up a semiconductor, it starts generating some heat, and as it generates heat, then it starts creating the thermal activity. If you've ever had an amplifier that crackles and pops and makes all kinds of noises, typically that is in the movement of these electrons and holes, carriers that occur. So let's now consider the condition known as saturation. When the base current is increased, the collector current also increases and VCE decreases as a result of more drop across R sub C. When VCE reaches a value called VCE sat, the base collector junction becomes forward biased and the collector current can increase no farther even with a continued increase in the base current I sub B. At the point of saturation, the relationship then, relation I sub C is equal to beta DC IB, is no longer valid. For a transistor, the voltage collector to emitter SAT occurs somewhere below the knee of the collector curves and is usually only a few tenths of a volt. Usually V sub CE SAT is assumed to be zero for analysis purposes. So a saturated transistor ideally acts as a short from collector to emitter. So let's look at something called the load line operation. We can see down here in the diagram we've got this line in here with something called the Q point. A straight line drawn on the collector curves between the cutoff and saturation points of the transistor is called the load line. Once set up, the transistor always operates along this line. Thus, any value of collector current and the corresponding voltage collector to emitter will fall on this line. Notice that the load line is determined by the collector circuit resistance and VCC and not the transistor itself. Now let's set up a DC load line for the circuit to the left here. First, determine the cutoff point on the load line. When the transistor is in cutoff, there is essentially no collector current. Thus, the collector emitter voltage, VCE, is equal to VCC. In this case, VCE is listed as 24 volts. So we can see that on the top here, VCE 24 volts. Next, determine the saturation point on the load line. When the transistor is saturated, VCE is approximately zero. Actually, it's usually a few tenths of a volt, but zero is a good approximation. So, good rule of thumb. Therefore, all the VCC voltage is dropped across R sub C and R sub E. So we can see that R sub C and R sub E is where your current is going to flow, VCC to ground. From this, you can determine the saturation value of collector current I sub C sat. This value is the maximum value for I sub C. You cannot possibly increase it any further without changing VCC, R sub C, or R sub E. in the figure, the value of IC sat is VCC divided by RC plus R sub E, which is 34.8 milliamps if you do the calculation. Finally, the cutoff and saturation points are plotted on the characteristic curves in the next diagram here. So on the bottom here. So let's crank this up a little bit here. There we go. Finally, the cutoff and saturation points are plotted on the graph, and a straight line, which is the DC load line, is drawn between the points. So between 34.8 milliamps saturation down to 24 volts cutoff is our endpoints for the load line. In the center here, we're going to find out what this Q or quiescent point is. So the Q point, the base current I sub B, is established by the base bias. The point at which the base current curve intercepts the DC load line is called the quiescent or the Q point. So we have the VCE intersecting with the load line, that gives us our Q point. The coordinates of the Q point are the values for ICE and VCE then at this point as illustrated. Okay, AC operation of an amplifier. If we look at the diagram below, okay, so you can see this looks pretty much like what we saw the last time here. Signal AC operation. In the circuit, an input signal produces an output signal with the same waveform as the input signal, but with greater amplitude. So we're going to put a tiny signal in to the base of the transistor, and then on the output here from the emitter to the collector, we're going to get our larger or amplified signal. This increase then is called the amplification. The figure shows an input signal Vn capacitively coupled to the base. The collector voltage is the output signal as indicated. The input signal voltage causes the base current to vary at the same frequency above and below its DC value. This variation in base current produces a corresponding variation in collector current. However, the variation in collector current is much larger than the variation in base current because the current gain through the transistor. So let's roll this up. The ratio then of the AC collector current I sub C to the AC base current I sub B is designated beta AC or HFE. These little HFE H values are normally used in the modeled circuits for a transistor, and they don't look anything like what you're looking at above. So beta AC is equal to the collector current divided by the base current. And you'll notice they've switched to lowercase script. Again, lowercase script telling you that it's an AC signal. The value of beta AC differs only slightly from the beta DC for a given transistor, and data sheets do not always show this parameter. Remember that lowercase subscripts, so here we are, distinguish AC currents and voltages from DC currents and voltages. Signal voltage gain then of an amplifier. And so you can see what we were talking about here. On the base, we have a small amplitude signal, V sub B, being input onto the base, and at the output, we've got a much larger signal. So if we take a look at the amplifier then and examine its voltage gain with a signal input, the output voltage is the collector voltage The variation in collector current produces a variation in the voltage across the resistor R sub C and a resulting variation in the collector voltage. Okay, so there we go. As the collector current increases, the I sub C RC drop increases. The increase produces a decrease in collector voltage because V sub C, small c, is equal to VCC minus I sub C RC. So you've got to keep track of these subscripts because some of them are DC and some of them are AC. Likewise, as the collector current decreases, the I sub C RC drop decreases and produces an increase in collector voltage. Therefore, there's a 180-degree phase shift between the collector current and the collector voltage. And we can see what's going on here. We've got a phase shift that's occurred from here and the input. This 180-degree phase shift difference then between the input and the output is called an inversion. The voltage gain, A sub V, little v in this case, of the amplifier is V out over Vn. So we're seeing this relationship again of output over input, much like we saw earlier when we did decibels, where V out is the signal voltage at the collector and Vn is the signal voltage at the base. Because the base emitter junction is forward biased, the signal voltage at the emitter is approximately equal to the signal voltage at the base. Thus, since V sub B is approximately equal to V sub E, again the AC values, the gain is approximately V sub C over V sub E, or IC RC by IE RE. Because the alpha AC is close to 1, I sub C and I sub E are very close to the same value. Therefore, they cancel, giving the voltage gain formula for the amplifier. And so there we go. A sub V approximately equal to R sub C over R sub E, the DC values. A negative sign on A sub V is often used to indicate the inversion between the input and the output. So we've got an example here. They want us to look at the signal voltage of 50 millivolts applied to the base of this amplifier. Determine the output signal voltage for the amplifier. Find the DC collector voltage on which the output signal voltage is riding, and draw the output waveform. So we take a look at the circuit here. We've got beta DC at 150, VCC is 25 volts, and we've got input, output taken across the collector. So the signal voltage gain, A sub V, is approximately equal to RC by RE. So we've got a 10 k ohm by a 1 k ohm resistor. So the signal voltage gain is a gain of 10. Notice there's no units because they cancel out. The output signal voltage is the input signal voltage times the voltage gain. So V out is AV divided by Vn. 10 times 50 millivolts gives us 500 millivolts, in this case RMS. Next, find the DC collector voltage. So VB approximately equal to, there's our voltage divider formulations again, R2 over the sum of R1, R2, VCC gives us 2.27 volts. I sub C then is approximately equal to I sub E, which is equal to the ratio of VE to RE, which is equal to V sub B minus 7/10, our barrier voltage, divided by 1 k ohm resistor, which gives us a current then for the collector 1.57 milliamps. Then the voltage drop for the collector, VCC minus ICRC, is equal to 9.3 volts. This value is the DC level of the input. The peak value of the output signal then is given as V peak is equal to, there's our relationship, 1.414 times the 500 millivolts. What was the 500 millivolts? RMS. 500 millivolts gives us 707 millivolts. C then says for the figure it shows the output waveform of the signal voltage riding on our 9.3 volt DC level. That's what we calculated there. V sub C, 9.3 volts. Remember, the output waveform is inverted compared to the input. So there's our simple sinusoidal output for that circuit. So when we come back, we'll take a look at the signal operation then on the load line. And so you can see what's going on here on our output signal as we see the operation in the active region.